Okay. Welcome everyone. Welcome to Harvard CMSA Quantum Mapping in Mathematics seminar series. We are delighted to invite Cheryne Jonay from Stanford University. She studied previously at the Princeton University and the Permit Institute for Theoretical Physics. And she has done interesting work on thermalizations and quantum many-body system. She'll be speaking about physical theory of two-stage thermalization. Please, let me remind the audience, please feel free to ask questions and interact with Cheryne during the talk. Let's welcome Cheryne. Thank you.
Thank you for inviting me, for having me today. So as announced, I'm going to be talking about the physical theory of two-stage thermalization. Emphasis should be on physical theory because the phenomena of two-stage thermalization was observed by other people, so this existed before. And this is work done with Tianji Zhu, who was at MIT until recently, but just moved to Virginia Tech. Yes, and as Ruben said, please ask questions because I actually prepared a shorter talk, which I think nobody will be upset about. But yeah, feel free to interrupt and ask questions at any point. So now this is not. 5 minutes.
Yes. Great.
Okay, good. Sorry. Okay, some background on thermalization. Basically, the setting that we're interested in for today is we consider one-dimensional systems with some degrees of freedom, which in this picture are just spins of qubits. And the sort of usual setup that's also relevant for experiments nowadays is that you start with a simple state psi that usually has no entanglement and very simple correlations, if any. And then you, can you look at the chat?
Oh, no, I just ask everyone.
Okay, great. Good. Okay, and then you time evolve your system with some unitary, which you can take to be either some exponential of the Hamiltonian, if you consider a system with energy conservation, or you could directly consider your unitary to be a quantum circuit, which I've shown here in sort of a tensor network representation, where you take your vertical degrees, your vertical axes to be the input, which in this case are spins. You act with some unitary, you get some output. And for those not familiar, there's a very nice recent review on quantum circuits and why they're important in our field nowadays here. And sort of just to motivate it for today's talk is that a few years ago, it was realized that you could study quantum dynamics by stripping down the dynamics to consider sort of the essentials of quantum mechanics, which is to have unitarity and locality, but you get rid of energy conservation. So you don't have a set of eigenstates or eigenenergies anymore. You just consider systems which have these two properties. And in fact, now people have even started stripping this away in the sense that they put in measurements in these circuits, so they only keep locality. But for today's talk, we're strictly looking at unitary dynamics and mostly just at quantum circuits. Okay, good. So then you start with, say, the simple state, this product state at some time 0. You time evolve it and you generate entanglement and correlations. So when you want to ask how close the state is to being thermal, you can't look at the full state because, as I said, we're doing unitary evolution, which maps pure states to pure states. So you go in and instead you ask questions about the subsystem. And you can basically think of the big quantum system as acting as a bath to the subsystem. And so you look at properties of this reduced density matrix when you want to study thermalization. A sort of experimentally motivated thing you could do is you could compute expectation values of local operators in this density matrix, and you can compare them to the thermal prediction by looking at this thermal state, and you want this difference to go to 0. Or you could study a entropy, which is basically just the log of the trace of the nth moment of this reduced density matrix. The n here is an integer. And when you take the limit as n goes to 1, this gives the familiar Feynman entropy. This arrow here is just to indicate that essentially it's the buildup of entanglement that lets the local expectation values equilibrate to the thermal prediction. So that's thermalization of pure states in a nutshell. When we talk about entropy, what entropy are we looking at? In this case, entanglement. So again, I wrote down the formula for the nth Renyi entropy. And it's been shown in many works that for what I will call generic systems, so specifically It applies to free theories, conformal field theories, and these random circuits we're going to be talking about. And it's conjectured to apply to chaotic systems without conservation laws. This entropy grows linearly up to some saturation time, which depends on the system size, at which it saturates. And the saturation is just an artifact of considering finite systems, so your entropy can't grow unboundedly. So this is the cartoon for entropy growth, some regime of linear growth and saturation. Now, the quantity we're going to be mostly studying today, and it will become clear why shortly, is the purity. So that's essentially just taking this trace rho A squared without considering the log. So you have 2 copies of your state, and then the correspondence of looking at the purity based on looking at the Rényi is just that it starts at 1, because initially if you have a product state, every subsystem is pure. And then it decays exponentially. So if the entanglement grows linearly, the purity decays exponentially up to some asymptotic value. So the question you can ask now, is this really the full picture of thermalization, right? This is a pretty simple image. You reach some saturation time, again, depends on the system size, and then your system is, at least at the superficially, it looks like it's thermalized. But there's been a lot of activity in the past years at looking sort of at physics beyond this saturation time. So one
Can I ask a quick question?
Maybe there's a
yeah.
Let's see. Okay.
Yes, how does the saturation time depend on system size?
Usually it scales with L. So usually it grows with L, at least in models that are local. Yeah.
Okay.
Yeah, you could just think simply of having in this picture here, you can think of having to act basically on all qubits. You entangle 2 of them at a time, so usually it scales with L.
I see. Yeah, makes sense. Thanks.
And that, oh, sorry, that's also a function of obviously the subsystem size of A that you consider here.
Yes.
Yeah.
Like thinking back to the last slide.
Yeah.
Yeah, like so I think that's kind of caveat also. Like it's true in free theories, but free theory does not promote us.
Free theories, it's just like free Fermi propagation that generates. Yes. But in a finite system, it's just saying, right, that you, I mean, again, this is me saying thermalization means I'm picking a quantity to look at, which in this case is entanglement, and I'm associating that with thermalization. That's, you can look at other quantities to study thermalization, which is what I will talk about in a second. So I guess ideas of deep thermalization, but you're saying, I mean, this has to saturate at some point if it's finite.
Yeah.
Finite, yeah, both.
It should be a low. You can think of entangled states that are not there.
Yes.
The system could be driven some entangled state and you have nothing to do with thermalization.
Yes, but I think it's more saying that the requirement, like thermal states, usually have entanglement. Of course, yes, exactly. And also you have exceptions, like, I mean, quantum stars, which are actually high energy states, which have lower entanglement with volume loss. So there's many examples. This is just sort of, there's many, again, this is not always true, but this is in the random circuits that we'll be considering, this behavior is there, and that's kind of all we need because we need this exponential decay of purity. So you can really think of it, at least for random circuits, this picture is true. There's obviously other systems for which it's not that easy. So yeah, if you want to look at physics beyond the saturation time, this is one thing to look at, which has been more popular in the high energy context, is this idea of complexity. I think this was brought forth in this 2014 paper by Lenny Susskind. And the simple idea is just that you could again have 2 states with very similar entanglement, but they can have very different complexity, where complexity is just the depth of the minimum quantum circuit that generates these states. And all that's saying is that while some quantity that you look at, like entanglement, saturates at some order L time, and you're done, this complexity, if you consider it's, I divided by the asymptotic value, it also plateaus at some point, but this time scale is much, much longer. So that already indicates there's some physics that goes on beyond the saturation time, and that's more than just entanglement. An alternative idea, which again, at least in my field, has been actively studied in the past years, is this idea of quantum state designs. So here, the idea is just that if you were to consider your state as some variable from a probability distribution, and you want to compare this to the thermal probability distribution, so to speak, you want to look that not only the first moment matches, but that all the higher moments matches, so that you can identify all the moments with a given probability distribution. And so you could think of your states that you get from time evolution. If you start with some different initial states, you time evolve them as generating an ensemble, or you could consider your ensemble of eigenstates. And then you want to compare to the Haar measure. And the Haar measure is basically the uniform measure on the unitary group. So it's the simplest, I guess, yeah. It's the simplest measure you can pick to compare when you don't have symmetries and you just want a benchmark. And then finally, you can look at higher moments, or I'm sure there's more, but finally in this list of examples, you could look at higher moments of the entanglement entropy itself. And essentially that's zooming in on this plateau here and looking at the fluctuations and seeing if there's interesting physics still beyond this point here. And that's what's most relevant to the talk today, because in these works that were pioneered by Ben Zenz-Nidarch in this series of papers, they show that if you look at the convergence of the purity to its asymptotic value, in a large class of systems, this actually happens as a two-stage process. So there's a first stage decay, which is set by some R1. Okay, this is exponential decay. That's why I said it's important that we consider systems where the entropy grows linearly. So there's a first stage decay set by R1, and then there's a second stage decay set by R2. And I just drew two lines to show you that in different models, we have two scenarios. You can have the scenario where your thermalization initially happens slowly and then speeds up, or you can have the opposite. And this first scenario in their studies was understood as, they called it a phantom eigenvalue. I'm not sure if this is their language or if it's an official term for spectra of non-Hermitian matrices, but they were studying this quantity here in terms of a transfer matrix. And so when you want to study thermalization in terms of the spectrum of this transfer matrix, the largest eigenvalue is going to be 1. The spectrum is bounded. So the largest eigenvalue is 1, which is the steady state. So when you want to look at the decay of the purity, you would go in and look at the second largest eigenvalue, and that's your theoretical prediction for what this decay rate should be. But what they found when they looked at numerics is that actually in finite systems, this first stage decay is not given by the second largest eigenvalue. Instead, it's given by an eigenvalue that lies in the gap between 1 and the second largest. And I think that's how it got its name, to be a phantom eigenvalue. In our theory, we're going to explain this phenomenon as a geometric effect. So it's basically going to be, we're going to see very concretely in the systems we consider, there's a boundary condition that's going to lead to this phenomena in terms of a geometric effect. Question? Yeah, I mean, it's not, I guess so they have a spectrum, of some transfer matrix that does the evolution on your state. So you could say you have some eigenvalue 1, and then you have some second largest eigenvalue, and then the rest. And you would think that the decay is given by the second largest eigenvalue. But what they actually find is they do numerics. So they simulate this purity decay, and then they extract this based on numerics, and they find that the decay rate is given by some other number. So this is just a number that sets the decay, and they say this is a phantom because it lies in between these two. And I think this is pretty well understood in the spectra of non-Hermitian matrices. I'm not sure. Yeah.
The original spectrum, these are Hermitian matrices. Like those that are real numbers.
No, in the case, no, this is non-Hermitian. Yeah, because the dynamics we're going to consider, I'll show this in a second, are in terms of some effective degrees of freedom, so they're no longer unitary. Yeah, so this is non-Hermitian.
I think that was the same. Yeah.
And then in other classes of models, you have the opposite scenario where you can have the first stage decay being larger than the second stage. And there was no understanding in terms of this transfer matrix before. And our theory basically is going to explain this as a competition between two effective modes. And depending on which one of them wins, that sets the second stage decay. So the plan for the rest of the talk is we got some background now, we define thermalization, and we also define the problem that we're interested in. We have to look at this idea of membrane theory, which is a way to study entanglement in terms of a minimization problem. And this will be important because then we're going to go to study the staircase geometry that I mentioned that has this this geometric effect. And then we'll look at the brickwork geometry, which has this competition of modes. But to understand these two phenomena, we need to have some tools at hand, which come from this membrane theory. And then up to here, this will be considering average dynamics. I'm going to be taking some average and considering dynamics in some effective space. But then we want to ask the question, does this apply to real life clean systems as well? Where, for instance, also you bring back in periodicity in time, so flow-K systems. And then finally, I'm going to give you sort of a more practical motivation for studying this, which is that you can measure entanglement from a local correlation function using this procedure. Okay, so actually, sorry, I have to membrane theory. So there's two aspects to it. So I got one. The first one is to try to study entanglement using some coarse-grained intuition. Okay, so entanglement entropy is notoriously difficult to measure and to calculate in many theories, also in practice. And so in these works listed here, especially by these first two lines of authors, is that they ask the question, or I don't know if they ask the question, that's how I interpret it, can we map this to a simpler problem? And the resounding answer, and maybe surprising, is that it's yes. You can write this entanglement entropy as a minimization problem over the, basically you're looking for the minimal cut in the tensor network representation of your unitary. So that's what's shown pictorially here. And you can actually just, if you want, drop the n index here because it's it applies to all entropies. You can see again, even if you take this t outside, you have the linear growth, and then you have just some prefactor, which is model dependent. And so the setup is that in this case, I just drew the same picture as before, but for two-side gates to show that basically that what a circuit does, it acts on two qubits, which are at time 0 unentangled. It usually then entangles them. Of course, you have some gates that can lower entanglement when you already have some, but statistically speaking, it's going to increase the entanglement. And so when you look at this problem then of having some unitary, you can either trotterize it if you started with a Hamiltonian system. If you started with a circuit, it's already in your circuit representation. You start with partitioning your system into A and B, and then you consider this minimal cut through this tensor network representation. And this epsilon of V here is what's called a line tension. So that's this object here. And this line tension basically is an energy function of your path through the circuit. And it depends on the velocity, or should be an anti-slope V at which you cut through. Okay. And you can prove this again in random circuits, and it's conjectured to apply to other systems as well, but there's just numerical evidence there. So again, from this coarse-grained perspective, is yes, you can study entanglement by looking at a minimal membrane through the circuit, and this also applies to higher dimension. It's not just a 1D statement.
Sorry, so, just a quick question.
Yeah.
When you say it's a minimal cut, are you cutting bonds, like the gray lines there? I think the line goes through.
Yeah, sorry, you're right. I should be cutting through bonds, not through the
bonds. Okay, I just wanted to make sure. Thanks.
So good. So I keep talking about random circuits and this Hart average. So let's look actually at a concrete example of what this does to our physical disease. So we look at this example quantity, the purity. This overlying specifically, we're taking the Hart average. So the purity contains two copies. So this red one would be U, U as U dagger, U and U dagger. And then the way to couple them correctly to denote that your spins are in A is you take this type of construction, which is denoted by a plus state. For being in subsystem B, we call this a minus state, and that's just a different type of contraction between the two copies. And when we take this average now, because we have dynamics that are independent in time, so you can think of these gates at each step being sampled independently from the Hart measure, the average factorizes in this direction. We also consider dynamics to begin with that are disordered in space, so it also factorizes in this direction. And so essentially you're left with a circuit where you have to consider this average over U4 over a two-side gate. And this is known exactly based on some Weingarten calculus. So you, again, here it's drawn these four copies of U, you take the average, and you end up with two effective degrees of freedom, sigma and tau, acting on these two sides. And now you see why the purity is especially easy because you have two copies. So you get two, so these 2 degrees of freedom are spins, are binary. In the case where you had more copies, so higher Renyi entropies, you could still have these 2 degrees of freedom, sigma and tau, but they would now each be elements of Sn, the permutation group on whatever number of copies you have here. So the problem gets more complicated. Yeah, so for purity, this is pretty easy. The only thing is they're combined by some weight here, which is a function of your local Hilbert space dimension Q. These are known as Weingarten functions. Find them on Wikipedia. There's a whole list of them. For the unitary group, they're pretty convenient. So yeah, the takeaway is that we get some new effective degree of freedom by taking this average. And what's nice is that we started with these plus minus states on the boundary, and we end up now, so initially these lines in the bulk of the circuit were physical spins, but when we take this Haar average, we end up with these plus minus states everywhere in the bulk as well. In the first step, I showed you have both sigma and tau degrees of freedom, so this lattice here doesn't look too appealing to begin with. So, okay, you mapped it to something nice, but this doesn't look like an easy partition function to evaluate. But the very nice thing that happens is that actually they show in these works, you can integrate out one of the degrees of freedom, and you're left with a very nice lattice that only contains the sigma spins. Okay, there's some plaquette term here that comes from integrating out the tau, which is a function just of these three sigmas. And so you're left then here with this geometry where you have a sigma, sigma, sigma. You add on these two. Next layer, you add on alternating bonds, and you can rewrite this very nicely as a circuit where now the whole circuit is given by these plus minus states, which again, they're actually operators. So they're just contractions that they're essentially pairing degrees of freedom between your copies. So that's the circuit representation. Again, it looks similar, but again, to emphasize these are different degrees of freedom. And as we've already discussed, this matrix M here is not unitary, but it's going to generically be some non-unitary matrix. Okay, are there any questions about this mapping? So we then mapped our partition function when we take the average to a statistical mechanics problem. And in this case, where you take the Haar average over two sites, the problem is actually extremely easy, because if you think of what the local dynamics are of the effective degree of freedom, these update rules are very simple. So if you have a plus plus state, you act on these two, you can only go to plus plus. If you have a minus minus, you can only go to minus minus. So that's the constraint that comes from unitarity. Then if you consider the spin, so you have Q equals 2, the Haar average based on this Weingarten calculus tells you that when you act on a bond like here, you have a plus minus, what you can do, the only step is to move this domain wall. Okay, so you act here on plus minus, you can either move this to the left or to the right. And this happens with some weight 2/5 that comes from this Weingarten function, but it's equal to the left and right. And so then you immediately see that this essentially collapses to considering all the domain wall trajectories through the circuit, and there's only order L of them, and that's already the end of the problem. So this greatly simplifies all the configurations that you have to consider. And so we've discussed now two ways to calculate purity when we using this membrane picture using this membrane picture. So the first one is you start here, you consider the microscopics, you see that the weight at each step is 2/5. You take T steps going from the boundary here at T down to 0. You consider all directed paths, that just gives you a factor of 2 to the T. So essentially this purity decay goes as 4/5 to the T. Alternatively, we said you can get it from coarse graining. I didn't show you what this energy function looks like here as a function of V because it's a bit complicated. But when you zoom out on this path, you can kind of tell that this path, this optimal curve is going to look straight because the unbiased random walk doesn't go very far from the origin. So when you zoom out, this line is going to look straight. And this energy, this line tension is minimized then at 0 velocity. And then you can plug this into the formula for the purity. And using both those methods, you see that for these brick wall circuits with the Haar average, you get purity decay in one stage. So that's the end of the story, and that's all you see. Yeah. Good. So now that we have this set, we're going to look at a different geometry, which is the staircase geometry. And this is where we know, based on these previous papers, that there's actually a two-stage decay. So the only thing that happens when you consider the staircase geometry is that essentially the circuit here, that's just showing the cartoon version, gets tilted. So the way you're acting now on your degrees of freedom is the staircase. And you can immediately see how this is going to change the optimization problem. Because whereas here, the shortest line was the one with 0 velocity, in this case, the shortest path exits your circuit at a slope. So it would be something that exits here. So this comes at a non-zero velocity, and so you can tell that this optimization for this geometry is going to be a competition between the shortest path and the cheapest path. And we can write this out pretty simply. So the free energy in this case is not only a function of the line tension, but it also considers the length of the path. And if you minimize this over v, you find that the optimum velocity has 1/5 instead of 0 as before. You can plug this into the expression for the purity, and you find that this first stage decay is given by square root of 2/3, which is what they had found in these earlier papers based on this phantom eigenvalue. So this phantom eigenvalue was this non-existent decay rate that wasn't given by the spectrum, the transit regions. So that's what happens in the regime where your time t is shorter than the saturation time, because then this geometric effect actually matters. Now, if you elongate the circuit, you can see that this aspect ratio really changes. And in this case, what we have to do is we divide our partition function into two parts. One of them is the trajectories that are going to exit at either one of the left and right spatial boundaries. And this essentially gives us the asymptotic value, because right, this is not going to change with time. The only thing we have to account for is the correction for the trajectories that do scale with time, which is the ones that lie exactly here, the light cone. Those have velocity or anti-velocity t over L over 2. So that's the subtraction here. And then we have another part, which is the bulk part, which is going to consider all the trajectories that roughly have velocity 0 because they go pretty much straight down. The important thing is that they exit at the t equals 0 boundary. And so in the large t limit, this free energy is much larger than this one. So in saddle point, we can essentially drop this term, and we're left with the asymptotic value plus this line tension at 0. And so z minus z asymptotic is going to give us exactly this decay here, which tells us that the second stage is given by the value that we saw before in the brickwork geometry. And that kind of makes sense, right? Because if you consider like this long of a circuit in the bulk, it doesn't know about the boundary effects, whether this is tilted or not. So we just get back the result that we had before for the brickwork geometry. So this basically is a summary for the staircase geometry and why you expect two-stage thermalization in these types of geometries. So now let's look at the brickwork geometry. So I already said when you take the Haar average over these two sites here, you don't get a two-stage decay. Okay, so then everything is given by this domain wall sector. However, if we consider more generic two-body interactions, which you can parameterize in this way, you can write any two-qubit gate that is down on 4, it has 16 degrees of freedom. You can write it in terms of 4 single-side qubit rotations. They're part of SU2, so they each have 3 degrees of freedom. You end up with 12 from these single-site rotations. And then you have a symmetric 2-qubit interaction, which you can parameterize in this way, which contains basically 3-parameter AX, AY, and AZ. These are sigma X, sigma Y, sigma Z operators. And then you have an overall phase. So in total, you have 16 degrees of freedom for the most generic 2-qubit gate. Now, we're still going to consider dynamics that are averaged locally over single-site rotations, because we look at things like entanglement, right? We're not really interested in, like, this is a sort of basis-independent quantity in terms of local qubit rotations. So we're going to still take the Haar average locally, and that leaves us initially with 3 parameters for this gate. But we're going to go even further and actually consider a special case where AX, AY is equal to 1, and we have a 1-parameter family of gates that's parameterized by this ZZ interaction. And these gates have the additional property, they're special because they're dual unitary. And what that means is that your dynamics are unitary not only in the time direction, but also in the space direction. And the only thing that's important there, we'll see later on, is that it really simplifies calculations of correlation functions because they can only live on the light cone. So usually when you have unitarity in time, your correlation functions, right, can exist anywhere inside the light cone, on the light cone. But when you have unitarity in time and space, you're strictly confined to the light cone. Okay, so that's a simplification for calculating. And yeah, so it was shown that in these systems that are dual unitary, the entanglement entropy, again, grows linearly, and it's independent of n, actually, in this case. And so the first stage decay is just this rate is 1 when you have an open boundary and 2 when you have a periodic boundary. It's just when you have a periodic boundary, right? Each time step you can entangle at 2 points. So entanglement grows twice as fast, or purity decays twice as fast. And so the more surprising thing, again, is recent development is looking at the second stage decay. And in this work by Benz and Sudarsh, they show that the decay rate as a function of this parameter AZ has this sort of smooth curve when you look at the periodic system, and it's capped and has this smooth part as a function of AZ. They conjectured this function, okay, of how this decay rate scales with AZ. And I guess some important points to point out in this phase diagram are when AZ equals to 1, this gate here, you have 1, 1, 1, is just a swap gate, so it doesn't generate any entanglement. So your second stage decay is 0. In this case, actually, this side is 0. And instead, if you have AZ equal to 0, you get an I-swap gate, which people have shown has maximum entanglement power. So this is something that generates a point. Good. So in these models, what are the new microscopic rules? So we saw before, we still have these constraints by unitarity. And we had before, we had the propagating domain wall, which we still have. So plus minus can still go to plus plus and go to minus minus. But we also have additional microscopic moves that are allowed, namely plus minus can just stay stationary. So it can go to plus minus to itself. Or more importantly, it can swap. So you have some local swap in terms of the effective degrees of freedom, which is going to be a very important move because essentially you still start with a domain wall if you consider half system purity. But now, based on the swap, right, you can generate a whole array of configurations in this partition function that you have to consider. So the problem kind of blows up in terms of complexity from being confined to the domain wall sector to suddenly having to consider this full exponential in system size number of configuration. And the mode that's going to be important, we conjecture, in the second stage decay is this magnon mode. So it's a bound state of the domain wall. It's basically it's a local mode as well, but instead of, again, the domain wall, it's just a single spin flip at some site. So it's a local mode. Good. So again, to account for this partition function, the full partition function, you would write it as this expression here. You have now some inside this light point here. You have to consider all the configurations. I just drew some out to visualize it. We still have this propagating domain wall that we had before. But we now also have terms where you have a domain wall and you locally, based on the swap, generate a magnon. And so you have a combined state between a magnon and a domain wall. And the game is now going to be basically to conjecture which configurations sort of contribute most importantly to this whole partition function. And so what we find is that the magnon, so when it's created in the bulk, what you end up with is free energy that's a combination of the domain wall and the magnon. And this is always larger than the free energy of a single domain wall, okay? And these are just, again, minimization problems. So basically what that means is that in this setting where you create a magnon in the bulk, the first stage decay is always going to be set by the domain wall because this has smaller free energy. Now, when T hits saturation time, so that means that this domain wall, if it started here, it can reach the boundary. It can generate then a single magnon, which is now not coupled to the domain wall anymore. So you have this free magnon mode. And now it becomes a real competition between the free energy of the domain wall and the magnon. So in the second stage, it's basically whichever, this depends on the parameters of your dynamics, it's basically whichever one of these is smaller. And so then we want to isolate this magnon term. So we saw the first stage doesn't really matter because it's all about the domain wall hitting the boundary and then uncoupling. So we can kind of kill that overhead time. We don't have to watch this happen. We can directly place our magnon where we want it to be to get out the second stage decay. And so we consider a subpartition function, which consists of putting in this magnon at time 0. We evolve it for some time t, and then we sum over all the final t equals 0 configurations, which are a magnon as well. And we conjecture, or sorry, this is exact. We say that this is our magnon decay rate. We conjecture that this is what sets the second stage decay rate. And so based on numerics, which we do using matrix product states for very large systems, we can see in terms of this heat map, which is showing this partition function scaled by the maximum, as it does decay exponentially otherwise. We see that it has a dominant contribution precisely on the light cone. So that confirms the idea that the dominating contribution here is the bare magnon. And then it can obviously branch based on these microscopic rules, but sort of to leading order, this bare amplitude captures the second stage decay rate extremely well. And these parameters here are just parameters for the gates that we discussed before. So there's still these dual unitary gates. This is just one choice of the AZ. Yeah. And then so using this, we can now actually have this we have this prediction from before, this was conjectured. We can see in our numerics that even when we start directly with the magnon, we get this line that looks exactly the same as we had here, which confirms basically just the intuition that the second stage is set by a magnon mode. And the nice part is now I sort of advertise why these dual unitary gates are nice, because you can calculate correlation functions. So the nice part is that we actually managed to get this decay, this curve from before analytically using intuitions from dual unitary circuits. So the simplification that happens in dual unitary circuits is that when you start with a local mode like this, which you can think of as a local operator in your circuit, technically you would have to consider, if you're in a light cone, you would have to consider your dynamics in the full forward and backward light cone. But when you have unitarity in space, you can contract sideways as well, your quantum circuit. And so you end up with a channel that looks like this. And so this is essentially just a repeated element of the same transfer matrix in time. And this transfer matrix is really small. It's at most for qubits, you have 4 operators, 4 bases operating on each side. So this is at most a 4x4 matrix if you consider dynamics here. And so we can exactly show that if we consider this input mode here to be a magnon, the eigenvalues of this transfer matrix are 1 for the plus state, and then the other one that's decaying gives us the magnon decay, and we can extract this formula from the previous slide here exactly based on this diagonalization. Okay, so that's the analytic solution for dual unitary circuits, and so that sort of completes the full picture here of we've seen that this convergence of the purity to its asymptotic value happens as a 2-stage decay in generic systems. So in brickworks, where you consider this this class of 2-side gates where you don't take the average over 2, but only over single sides. And we've also seen this phenomena in staircase geometry. In this case, it's actually independent of your dynamics, but it's just a geometric effect. Okay, so this was all, again, average dynamics. So let's look at clean systems.
Can I ask a quick question? Maybe, hopefully quick. You said the second stage decay has, it depends on on the dynamics, whether you get the magnon or just the domain wall. Mm-hmm. Can you give some sense which systems have your talk is about the complexity of this situation, right? So is there something is there something that helps decide which of those two?
Yeah, it's whichever one has this, I guess, smaller free energy. So you have to compute this free energy of both of those modes, which I haven't shown how to do, but in general, that's how you do it. So whichever mode, so right, you're looking for the slow mode. What sets your thermalization in this case is the slow mode, and which one it is amongst these two is a function of this parameter. I'm considering on one parameter class of gates, so the only thing I have is AZ, and which one is slower, depends on this AZ. So you have some regions here, and in this region here, based on, where did I show that? Right. So here you can see these microscopic update rules, and there's for some values of AZ, you can see that the biggest transition amplitude comes from swapping. So you start with a domain wall to swap. For other parameters, values of AZ, you can still show that maybe the domain wall has a larger amplitude, and so the preferred decay would be given by the domain wall. It just depends which gate you pick, because that affects your microscopic rules. So you have to look at those, and then based on that, you can tell.
I see. So it's a very detailed kind of question, whether one wins over the other. There isn't like a simple qualitative understanding.
There is one simplification, which is that at this critical, to the left of this critical value, actually, for this set of gates, the domain wall move is preferred in this region. And you can see in this region here to the right is the swap that's preferred. So you can kind of ignore the configuration where nothing moves. So the important thing is the domain wall versus the magnon. And you can see to the left here of this critical point, it's the domain wall move that's larger, and here it's the magnon. But then there's a lot more phase space to explore, right? We're considering very specific gates here, which again have these this one we're scaling. But you could technically go into the whole landscape of gates, and you could look there, and there you probably have different modes that minimize the free energy, so that I don't. Yeah.
All right. Thanks.
Okay. So
actually, the analytic prediction that you quote this benzene is neat. I think this, yes. So this one describes which curve. Just make sure.
This one describes this curve here. So basically, it's, I mean, this is right. You can see the red dashed line is this analytic prediction, and the dots are data from matrix product state numerics. So they just collapse. So they had these numerics. They didn't start the configuration with the magnons, so they just considered regular purity decay path system, which at later time is given again by the magnon. And I think they just fitted this and saw this, or I don't know how they conjectured it, but there wasn't a proof for this formula. So all we did was just to use this transfer matrix approach from dual unitary circuits. And if you look at the spectrum, then of this transfer matrix, you can get this value. So you can already get a taste of how this is mapping this purity decay to a correlation function. But more on that. Okay.
So you have an input derivation from microscopic perspective.
Yeah. So this essentially just tells you this is just using, I didn't write it down, but it's using this M matrix that I said was just a non-unitary matrix. And this M matrix is a function of your local microscopics. And then based on this M matrix, you can diagonalize this transfer and you get spectrum, which tells you the purity decay. Yeah. So clean systems. So we kind of want to get rid of disorder averaging, because when we disorder average, right, your modes are confined in the bulk of your circuit to also be these plus minus states. So life is kind of easy up to a certain extent. So we now want to consider, for instance, we fix our single qubit rotations in terms of this parameter phi, and we consider the two-side interactions as before. So we can still use this transfer matrix approach as we did before, only that this time it's not going to be strictly confined to the plus minus sector. So you have to be a bit careful here. It's a 4x4 matrix, first of all, because of all the input operators. But we can still use this approach because we're still looking at dual unitary dynamics where your correlation functions are on the light cone. So even in this case, even without this order averaging with single sites, you can see that in these clean time periodic systems, the magnon mode still seems to dominate. So that's kind of reassuring, because then it tells us it's not just a special artifact of random circuits, but it occurs in these real life cases as well. And yeah, this is just showing you, for instance, based on this transfer matrix spectrum, it's very small, but you can get these numerical values for the decay rate, which are these solid lines. And then the dashed dotted lines are numerical computations of this prediction function, and you can see that these agree extremely well. When we go away from the dual unitary point, which is just this plot here, we don't have analytic prediction anymore, so we're just left with looking at the numerical decay. Okay, so finally, how could we use this for something, I guess, more experimentally motivated? The idea is to use this procedure to measure entanglement from a local correlation function. And the way to do this is you have to look at the reverse transition. So whereas before we started with a domain wall, in this case, you start with a magnon at some site. And the game is kind of the same. So for t smaller than saturation time, this magnon can generate a domain wall, but it has to exist on top of the magnon. And you can show that the free energy of this is always going to be larger than the free energy of the magnon. So in the first stage, the magnon is always going to win. But in the second stage, again, as before, you have a legitimate competition between the two modes. And so whichever one has a smaller free energy is going to win. Good. So To make this easier experimentally, we kind of, again, want to kill this overhead of having to wait until this mode reaches the boundary and then kicks off, because that takes a lot of time to run in simulation or experiment. So we can directly place our magnon here at the spatial boundary, and then we can immediately enter the second stage, okay, where it's a competition between the magnon and the domain wall. And as long as you pick parameters of these gates, we have to go into this parameter space of the gates. As long as you pick parameters of these gates where the free energy of the domain wall is smaller than the free energy of the magnon, you can get the second stage decay to be set by the domain wall. And so what you are really measuring is going to be a half system purity decay, but you did it using essentially a local mode, which you can then associate with looking at a local correlation function squared, okay? So this is, you can think of this minus state basically as a local operator. You consider this squared because, when we look at purity, we have 4 copies of U, so we need to look at something that also has 4 copies. But that's essentially the idea. Then the only thing you have to extrapolate is you have to say that this decay of this correlation function squared minus the saturation value, you identify this as the decay that also sets the purity decay. Okay? And that gives you direct sort of hands-on experimental access to measure the purity decay using a local correlation function. And yeah, that's my side. Thank you very much.
Any question on that?
Can you give me an intuition like how to construct such a system with a two-stage thermalization, say using this one?
No, I don't know right now. So this was, I should say this was observed in not just entanglement entropy, but also correlation, out of time with the correlation function, two-stage process.
Maybe you can show that slide.
Well, I don't have a slide.
Or maybe this system.
Yeah, I don't have well, the most generic system I gave you is this one. So I can't tell you. Also, the thing that happens when you have a Hamiltonian is you also have energy conservation. So this early time linear growth of entropy is already slightly different because we have diffusion of energy. So I'm not even sure if the functional dependence would be the same. Right now we have exponential decay in both regimes. It's just a different free factor. I'm not sure how that would translate.
Another question, right? What's the n capacity?
Yes, it's just the nth Renyi entropy. Yeah. So it's this formula from the beginning, but it's just saying for these dual unitaries, they're special. Usually it's this n. Usually this slope looks different when you look at different n. It's slightly different slopes, different saturation value, different saturation time. It's just that for these dual unitary circuits, I think the linear growth is independent of n. It's just t log 2 whatever n you look at.
So the entanglement spectrum is like
yeah. I think this is, you can check these works here. I think it should be in there. So yeah, they compute this in these 2 works.
And gets a little bit confused in the sense that just this matrix like does not have the flat spectrum. But in this case, you have a flat spectrum. Why should I integrate that as a thermalization?
I guess, okay, I don't know these words by detail, but I think you're saying you have, usually it's 1/n, so everything's flat in thermal density matrix, right? No, sorry, in a thermal density matrix, right, which is supposed to be identity, everything's flat.
Sorry. Yeah, like algebraically.
Yeah, there's no temperature in here again for circuits. Yeah, so flat is again, flat is the correct thing. It's just an idea.
I have another question. So I was, when you introduced the Haar average, it went a little quick for me, and later you got rid of it, right? And I was just wondering, why would the Haar average seems to convert the problem completely to a classical problem? So, so it almost seems like you're not really even doing a quantum, I guess, is that right? Is that the main concern about the Haar, or is there something still quantum about the Haar average problem?
But if you look at the microscopics, I guess you could argue no, because you go into this space where, again, you have these effective degrees of freedom, and then, it's a classical problem, but that's kind of the whole motivation for, mapping to a classical StatMech model. It gives you a problem that you can solve, and that's sort of what the Haar average buys you.
I see, but so I should really think of it as that you're trying to derive a classical model which has sort of similar geometry to the quantum problem. And see what you
want to do is you want to argue that generic chaotic evolution, it's very similar to Haar. So they do this in these papers here. I think the 2019 one is they consider sort of bubbles where now your spin degrees of freedom are not forced to be plus and minus anyone. So that's sort of simulating you not having taken this Haar average. Okay, so you have here. And they do some perturbative expansion in terms of this bubble size in generic chaotic systems. So you always have this domain wall here, just because you're looking at some half system purity. And then if you have some more generic dynamics, you argue they have one component which is similar to Haar because it's chaotic. So that gives you still the domain wall. But then you have some other states which they call S-perp. So they're perpendicular to these plus and minus states, and they can bound this in terms of sort of a perturbative expansion of this bubble size where you deviate.
I see. That's cool. So then they can show that just doing the average is kind of giving you a kind of dominant effect.
That's shown specifically in these works here.
I see. Thanks.
This may be a very basic question, so I apologize. But if you have this non-unitary matrix or another non-unitary matrix generically you have some symmetry, especially like a spatial symmetry, then wouldn't you expect to have some like configuration errors or any eigenvalues that have the imaginary component?
That's for the I think you're right. Yes, I think that so this one might be real, and then if they're complex, they have to be pairs. So I think you're allowed to have real eigenvalues. Again, I'm not an expert on this, but I think in these transfer matrices, you might know, I think you're allowed to have both real and imaginary eigenvalues. If they're imaginary, as I said, they have to come in pairs.
So how do you know that the second one is pure?
I think you don't know for sure. It's just they did the problem. It boiled down to this transfer matrix for this type of problem being very nice. So they could solve it. It was like Toeplitz matrix, so they could solve it in Chebyshev polynomials. And so they actually get this for any integer n. And I think it so happens that for this problem of the Haar average case, they're real. I know they've also numerically looked at it when it's not real. I'm not sure if the second largest is necessarily always real. It could be that maybe it's an envelope, an exponential decay with an envelope that fluctuates. That I don't know. I think this is a question also of whatever your input unitary is. Again, this map is not going to carry through in the same way, but you would want to map your unitary to some effective dynamics, like Jacobian dynamics, for instance, of your effective degrees of freedom. And depending on what your unitary dynamics are, I think it's going to look different. I can.
Any more questions, comments? If not, we should thank you again. Thank you.
Thank you.
Thank you.
Thank you.
Thank you for your questions.